let's remember that yesterday we looked at d-regular graphs, and we found a formula of the number of d-regular graphs for fixed d in terms of the number of pairings in the configuration model, and then a probability that a random pairing gives us a simple graph. Okay, and we proved that the probability of simple is this, asymptotically equal to this, when d is fixed, and we use the method of moments. And the method of moments really needs that these means, the lambda i's, are bigger of 1. Okay, so this like works only for, like, if you use this method of moment black box as a black box, then you can only do this for fixed d. But if you go into the calculations of that and you are more careful with the calculations, then that proof, the same proof works for d all the way up to root 2 log n. And that is what Bolobash did in that proof. And then what happened afterwards? So the probability of simple, so what McKay showed is that, yes, McKay showed that this probability of simple is actually equal to e to the minus d squared minus 1 on 4 plus big O of d cubed over n for any d, okay? So for all d, that's McKay. And this is, yeah, for all d. But of course, that only gives you an asymptotic formula if d is little of the third root of n. And that's why he used switchings. And then if you go one level more, like you ask, okay, what's the term of that order? So the final call on this is that the probability of simple is equal to e to the, let's write x of minus d squared minus 1 on 4 minus d cubed over 12n plus big O of d squared over n. Okay, and this is whenever d is little o of square root of n, and that was like McKay and Wormold in 1989. Now they proved this bound, or like the estimate on probability simple via like a very refined switching analysis, which I decided to skip. Like if we have time on Friday, I will show you how that works. But that's something that's available in the literature and has been taught many times. And anyways, like our proof will cover that range, the proof that we will show you. That is the formula for d-regular graphs. I also, if you did the last or second to last exercise on the problem sheet yesterday, you also found a way to turn this into a formula for irregular sequences. And let me give you this formula for that range, like the densest possible formula we know for the irregular case. So I write it out once, but mainly because there's a typo in the lecture notes. You do not have to remember this. So the general formula looks like that. It's like m1 factorial over 2 to the m1 on 2, m1 on 2 factorial, and then a product of the di factorial I equals 1 up to n. So that is where mi for I at least 1 will be the sum from, let me say k. So if I is an index here, of the di and the falling factorial of length k. Okay, so m1 is just the sum of the di's, that's just dn, like the average, where d is the average. But then, yeah, m2 is like a second falling factorial moment, and so on. So these moments come up in this formula. And the formula is this, exp of minus m2 over 2m1 minus m2 squared over 4m1 squared, and that is the typo in the notes. And then minus m2 all squared m3 over 2m1 to the 4, and then there come two more terms, m2 to the 4, well, over 4 m1 to the 5 plus m3 squared over whatever, 6 m1 cubed plus big O of d cubed over m1. Okay, so the reason I write this, like if you did this exercise yesterday, you may have guessed these first two terms by looking at the moments, at the expectations of loops and pairs of double edges. So that's just for you to verify. And then these are the more precise terms, and that works all the way up to here. So for regular, that gives you, that simplifies to exactly this formula. Okay, and that was, well, that's the same paper, McKay and Wormald in 89. Okay. So then you would like to know whether there's any combinatorial information in this. Like, why is that the sequence? And well, your guess is as good as mine, but what McKay and Wormald realized is that you can rewrite this formula in a different way. So we started right with the configuration model, and we had this factor E, and that was really good when D is really small. But if you, or let's, yeah, well, let's take this one. If D tends to infinity, right, then this probability tends to 1. So the probability of being simple actually gets smaller and smaller as D increases. And so maybe modeling the degree like a number of D regular graphs with the configuration model is not the right thing to do anymore. So the formula that they found, which is equivalent, is the following. And this I will refer to as just the formula, is that G of D is equal to n choose 2 choose m times the product I equals 1 from n minus 1 choose di over n times n minus 1 choose 2m times some factor, which is now a 1/4 minus, and here come new variables, a gamma 2 squared of d over 4 mu squared, 1 minus mu squared, plus little o of 1. Okay. Let me first tell you what mu and gamma is, and then we will digest this together. So the mu is simply the density of a graph with that degree sequence. So that's an m over n choose 2. Okay? And the and the gamma 2 is like a scaled variance. So that's like the sum over all I of di minus d squared 1 over n minus 1 squared. And d is always this times n. So m over n minus 1. So d is always the average, which is m over n minus 1. Okay? Yes, 2m over. Right? Sorry, I have a brain stop. Yeah, no, like, yeah, no, yeah, that should be m over n minus 1. Okay, so what does this formula say? So first, let's start with this n choose 2 over choose m. Yes? What is what? M? Oh, yeah. M is the, okay. M is always the number of edges. So that's always the sum of the di's over 2 times n. Over 2. Yeah. Does that make sense? Sorry, D is the average degree. D is 1 on n times the sum of the di's. D is always the average degree of a sequence D. M is always the number of edges of a graph with degree sequence D. Mu is always the density of a graph with degree sequence D. Yeah, and now I think I have defined all of these terms. Okay, any other questions?
Can you explain why delta cube over M1 is of higher order than the terms we've written down?
Delta cubed?
The formula.
Gamma cube, wait, sorry, what?
The formula at the top.
This one?
Yeah. O, in big O, delta cube over M1.
Over M1. Well, M3 is at most a D cubed times n. So you have a... So wait, you want to know for this term?
Delta cube over M1, why is that smaller than the...
It's only small if delta cubed is little o of M1. I mean, you're assuming that you're in that range. And if you have a regular graph, then that is just the D. D cubed is little o of dn. That's what this defaults to for D regular. So that is like a D squared over n, which is this error term here. Does that make sense? Yeah. Any other questions? Okay. So we have here an n choose 2 choose m. And if we divide, this whole, both sides by n choose 2 choose m, then what we see here is the probability that a random graph with m edges has degree sequence D. So probability that the degree sequence of G and M is equal to D is exactly equal to the size of G of D over n choose 2 choose m. Okay? So if we divide this, we see a probability. Now, what's that term here? So the term, the product I equals 1 up to n minus 1 choose d, I over n times n minus 1 choose 2m. Okay. So how can we interpret this? So what I claim is that this is the probability of the following thing happening. You have n boxes. So these are n boxes. And all of them have size of one box is n minus 1. Okay? So this is like your box B1 for the vertex, for vertex 1. Here you have n minus 1 in box 2, and so on. So that's the size n times n minus 1. Now, I throw in this whole arrangement 2m points or balls, and then I ask, what is the probability? So throw in 2m points, okay? And then I ask, what is the probability that I see exactly D1 in box 1, exactly D2 in box 2, and so on. Okay, so it's a, Dn in box n. So this one is the probability that in this model, I see the sequence D. Right? There are that many ways to throw in D1 boxes in D1 elements in this box, D2 elements in this box, and so on. And overall, I have n times n minus 1 choose 2m ways to distribute my 2m balls. So that model I want to call the binomial model, which has some n as well. And you can describe it equivalently as as like that you take n independent binomials with distribution n minus 1 p, some p, it doesn't take p to be 1/2, whatever you want, but you condition on, let's call them xi, condition on the sum of the xi to be equal to 2m. And if you condition on that sum, the p vanishes again. And the probability in that model is that you see sequence d1, d2 up to dn is exactly this probability. There are two ways to describe this model. Take whichever one you prefer. Okay, so what this formula says is so the formula is equivalent to the probability that the degree sequence of G and M is equal to D is equal to the probability that this binomial model gives me degree sequence D times some correction factor times this exp of 1/4 minus gamma 2 squared Okay. Now, let me tell you something about this correction factor. Of course, we cannot possibly assume that this formula holds everywhere unless these things sum to 1, because we have a probability there. Okay. Now, what can we say about this correction factor? Let's just simplify this as the correction factor. So what is the correction factor for the D regular? So if the sequence D has just D's everywhere, then what happens to this gamma 2? It's just 0. So that is simply e to the 1/4 plus little o1. Okay, so it tells you this independent binomials is wrong by a factor of e to the 1/4. You also notice that this is like maximal, right? E to the 1/4. So this gamma 2 is a square, and here, like this is a square, this is a positive term. So actually, this term is always at most e to the 1/4, and it's at least 0. But also what we may see in this course, but what you can show is that in both models, this factor is tightly concentrated around 1. So one can show that the correction factor is equal to 1 plus little o1 in both random models. Okay, so that means that for a sequence in G and P, for typical sequences, like it's actually, this probability is a really good approximation. Okay, but so, yeah, I will not show this now. I might show this later in the course. Okay.
Sorry, what do you mean within both random models?
random models in the degree sequence of G and M, and in this binomial model. Sorry. Yes. So in each of them, you show separately that this is tightly concentrated around, like this whole term, around 1/4. And like you do get something better than a little over 1 even. Okay. Yeah. Any other question? Okay. Good. So what does that say? So let's have a diagram. So what this says, like we have one probability model, which say this looks like a normal curve, which is, it doesn't, but let's say this is like some probability distribution, P1, and what this says, we are approximating this probability distribution by that much simpler to calculate probability distribution. So not everywhere, but it's equal almost or very close to this probability distribution on some really dense set where the most of the mass is. And then outside, like it's like something else. We don't know what it is. But the mass of this part is so tiny that we don't really care. Okay? Good. So that's how you should like read such a formula. Okay. Now, I just said that Mackay and Wormold realized you can rewrite that formula like that. And they also proved this formula for the very dense case. So when you rewrite whatever you get for the dense case and for the sparse case, and you can rewrite both of these formulas in this common form. So you have a formula which holds for very small n and for very large n, you conjecture it's true in the middle of as well. So the conjecture like a subset of the conjecture by Mackay and Wormold is that this is true for all medium densities. So let's write log n, let's say at most d, at most an n. That's the average degree. So like turn this in n times. So for m, this would be an n times log n at most m at most n squared. These two are equivalent. And not for all sequences, but only those that we see here. So we call them nearly regular. Nearly regular sequences. And these are sequences that satisfy like some upper bound on this max degree deviation. Okay, so like under the assumption that you're nearly regular and you're in this intermediate density, you are able to prove this formula. That was the conjecture. Okay. Good. So what we will do is that I'll show you an approach how to prove that conjecture under like more mild, a little bit milder assumptions, and the d not all the way up to n, but some small power of n. But yeah, so the goal is to show this formula for d being little o of, I think, n to the 2/5 over some log, and the deviation, let me just say nearly regular, and we'll see in a bit what we mean exactly. Okay? Okay. Any questions? Good. So okay, so we want, how would you, like in general, how do you want to approach to find a formula for the number of, like for the size of some, yes.
What is the state of the conjecture?
The statement is that when...
What's the state? Like what is known?
It's known.
It's
completely known. Yes. Yeah, that was a okay. That was a conjecture made in 1990 by McKay and Wormold. And it's now a theorem. Okay. Yeah, but we show a subset of the conjecture just to show, like, yeah, like to get you used to the method. I think the method is nice and might have applications in other ways where you have counting. And it shows some nice combinatorial ideas. Yeah. Okay. So that's our goal. For that range of D, I'll show you some proof of a weak version of the conjecture. Okay, so how do we want, say we want to count this G of D, but we already have seen, like we already went to this probabilistic view, this one actually here, that like counting the number of graphs with a given degree sequence is equivalent to asking what's the probability of that G and M has this degree sequence. And that is really a useful view. So if we want, instead of that number, the probability that the degree sequence of G and M is equal to the number of D regular graphs. So suppose I have here a set D of degree sequences. Then what this does is that it defines me a probability distribution on the set D. And what I want, what this probabilistic formula says is that I would like to find like some approximations by some other or like probability measure. So I want to approximate these by simpler to calculate probability. Okay, and that like has been done before. Like you have some complicated probability and you try to approximate it by a different probability measure. All we are interested is 1 point probability, but what we will get is a whole distribution because of this approach. So how do you show something like this? The trick is that you do not want to concentrate on a point probability, but on pairwise ratios. So if, say we find YDs for all D in this, whatever the set D is, such that if I sum the YDs over all these Ds in my set, and right, then I'll write equal, but yeah, let's say I find YD such that the sum is exactly the same as, let me call this XD for all D and D, and the pairwise ratios agree. So if I take XD over XD prime, then that's equal to my YD over YD prime. If I find that, then actually these two together imply, well, then XD must be equal to YD for all D in my set D. Right? I have my set D, and for every D I associate to this like two numbers, like an XD and a YD, and then I show that whenever I compare these two numbers for two elements in here, the pairwise ratio is the same, and I also sum to the same thing, then I actually get that pointwise they are exactly the same. And a version of this works with an approximation. D.
Curly D, yes. Those are the set of nearly regular degrees sequences?
It's just some set of degrees. Yes, it will be the set of all nearly irregular on. But we will make this precise in a moment. But it's just some set D, okay? And suppose you take, you could just think, I mean, this lemma, this ratio lemma is true even if D is all the sequences that sum to 2m. That's just like explaining the overall idea, okay? So the point is that if in the set D I get the ratios equal and they sum to the same thing, then they actually agree pointwise. Okay, I put this like a version of what we need as an exercise on a problem sheet. But we will not get exact equality. We will get some approximate version. So let's say you can do whatever proof you find for this. I can add here an error term. So psi is some number greater than 0. And if I add here this error term, I say, okay, these two sums are roughly equal. So both of these are 1 minus little o of 1, for example. And then I put, and I get the same error, a relative error for my ratios. But I need that this implicit constant is uniform for all pairs. So it's the same implicit constant C for all D prime in D. Then I get here this approximation with exactly the same error. Okay? Okay. So that's the overall idea. Okay. Any questions?
Is that error term supposed to be in the ratio as well?
Here, it's here.
Yeah.
Yes.
So there's no canceling thing going.
No, it's no, it's the same error. The way you get something like this is like, say you write, I can give you a hint. If you write the sum of all xd over, or xd prime over a fixed xd. And then you just like pull out the error. What you need is that it's the same error bound for all pairwise ratios, and then you get it. Yeah. Okay. Good. So what we want, right, like this hints that we want to find these formula YD, which also sum to the same thing. And so the pairwise ratios agree with the, okay. Good. So let's write our goal. Overall is find YDs. Find a set D and formally YD for all D in the set D such that we have three things. One is that the probabilities are in G and M. The ratios of probabilities in G and M, D prime, are equal to the ratios of these YDs, YD prime, times all we need here is a little of one error. That's our first, that's a ratio goal we want to achieve. Then we also want that the sum of the YDs is equal to 1 plus little o of 1 to the sum of these probabilities. And finally, I mean, we did want to say something about the deregular sequence. So we would also like that our deregular sequence, which is just constant D, is in our set D, right? So if we achieve that, if we find the set D and this approximating formula is YD, then we just look what is this D for our deregular one. But it's seemingly harder, but finding ratio approximations is easier than actually finding point probabilities. Okay. Okay, and what is this set D? Now we get there. So the set D is what we call dm. And this is like what someone said, like the typical sequences in GNM. Okay, so it's a set of all those D of length n such that the total degree is equal to 2m, and the deviation from the average is at most 10 root d log n. For all I. Okay. So that's what we will work with. This will be our set D, and that is nearly regular, means exactly that I don't deviate too much from my average. Okay. Now, what, why would we not want to work with the set D that is like say we forbid this condition. We just take all the set of all sequences that sum to 2m. Well, then we would have to say something about these probabilities for very rare sequences, right? And that's hard. So let's just concentrate on these. That set does include the deregular, and let's just work with that set. Okay. Now, what can we say about the sum of these probabilities of in GNM? For D in DM. Well, what we will say is that this is a set of measure almost one in my probability space. So that is 1 minus little of 1. Why? Has anyone seen these concentration results? No? Do you know that in GNP you are concentrated degrees? Yeah. Why would the same be true for GNM? Well, what are the degrees in GNM? GNM. What's the distribution of the degree of vertex I? It's a hypergeometric distribution with which parameters? So my whole universe where I throw in edges has size n choose 2. My horizon, what I see from a vertex, has size n minus 1. And the total number of successes is m. Right? So the hypergeometric distribution tells you what's the probability that, like, I see exactly k successes in my horizon when there are m successes in the whole world. Okay, so that's a hypergeometric. And what we need is like a Chernoff bound for hypergeometric. Okay. Okay. So the Chernoff for hypergeometric Chernoff inequality is as follows. If X has hypergeometric distribution of parameters capital N, capital K, and let's just keep the M, then the probability that X deviates from its expectation by more than like a delta times the expectation is at most 2 times e to the minus the minimum of delta squared and delta times the expectation of x on 4. Okay, so if, and this is just delta squared if delta is at most 1. Okay, so why would you believe me that something like this is true? Well, the hypergeometric, under some conditions, isn't too far from binomial. Like in G and P, the degree of a vertex is just binomial with parameters n minus 1 and p. The probability that I deviate from the expectation is by much is exponentially small. And for hypergeometric, we would expect something similar to be true. There are 2 ways you can prove this. You can either use Vatter's proof. Vatter's proof of the Chernoff inequality for binomial distribution that generalizes to hypergeometric, or or you show that the hypergeometric and the binomial distribution are, you can couple them with some martingale coupling. Okay. So these are, standard concentration inequalities. I will not prove this. I'll just assume this. But the important corollary that we get from this is that, let me just write the corollary, is that in G and M, the probability that there exists a vertex I such that di deviates from d by more than 10 times root d log n is at most n to the minus 23. And I forgot the conditions. I'll tell the, I write the conditions below. And while we are at this, we might as well do the binomial, do the same thing for the distribution for this BMN, which is also a hypergeometric with almost the same average, but exactly the same bounds. So you get, let me just say, exactly the same bounds hold under the condition that, what did I write for conditions? My conditions are gone, but I think you need something like a log n, like say squared times n is at most m, and I think that's it. But let's just say n over 2 as an upper bound. So, yeah. Sorry?
The left-hand side is bigger than the right.
Yeah. Yeah. Okay. Actually, I don't think you need a lower bound, just to say that the di's are concentrated around d. So for that range, this is lower order term of d, that's all. But I don't, for that, you might not even need a lower bound. Okay. Okay, good. So what that implies is that the probability of our dm is 1 minus big O of n to the minus 23, right? So, yeah, this one here. No, wait. yeah, the sum, what is the sum of these? Like it's just going to be 1 minus big O, or 1 minus little of 1, or 1 minus big O of n to the minus 23. So that will be our set D on which we estimate ratio probabilities. Okay. So, so what we want now is like a good approximation for ratios of probabilities on the set Dm. And we will not find, so, right, you want for any 2-degree sequences in the set, you want to know like how many, like what's the probability of hitting this versus the probability of hitting this. What we will do instead is we will look at local changes. Okay. Yeah. Any question for like the concentration of degrees? Okay. Okay. So we will get very precise formulae for the probability of, let me just say D over the probability of D prime when D and D prime are close. Oh. And so what is this local change I want to consider? So the local change I want to consider is the following. So take a graph G with degree sequence D, say. Then the vertex A has some degree dA. And here's my vertex B that has some degree dB. And I want to move, like pick a neighbor of A and move this over to become a neighbor of dB. Okay, so that switch, if it's possible, will give me a new graph where I don't have an edge here, but I do have a new edge at B. So here I will gain a degree, and here I will lose a degree. Okay, so that new graph, that degree switched graph, has degree sequence D, vertex A loses 1, and vertex B gains 1. So this is the unit vector with 1 in component A, right? Does that make sense? Okay. So these are the local changes that I want to consider. And so let me define the local change graph. S on vertex set Dm. Well, when do I draw an edge between two sequences if they are related by a degree switch? Okay, so D, and I draw an edge to D minus EA plus EB for any two sequences. Well, yeah. For D, I just look at all sequences I can reach by a local change, and I just draw an edge between those. Okay. Now, what can we say about this graph S? So claim 1 is that S is connected. Why would that be true? So on S, like what is my set Dm? It's all those degree sequences where the individual degrees don't deviate too much. So pick an arbitrary one and, well, look at the D-regular one, the D-regular sequences. Pick an arbitrary different degree sequence D and just switch all the degrees that are above D towards the D-regular one, and all with something that has degree less than D. And you switch towards the D-regular. So you show there's some path to the D-regular, and you do this for an arbitrary D, you're done. Okay, so proof is also an exercise, but what the same proof shows is something about the diameter of this S. So the diameter of S is at most, well, however many degree switches we need. For an individual D, we need at most that many to get it down to D regular. And yeah, so that is at most, let's say 20 times the root D log n. And I need to do this for every vertex. Okay? Right, and twice that because I go from 1 to the D regular, and then I might need twice as many to go back to another one. So that diameter is that, and the proof is an exercise. Okay. So the crucial lemma about these local changes is the following, which I call the crucial ratio lemma. Okay, for all D in dm and all A, B, and N such that D minus EA plus EB is also in dm, we have the following. We have the probability that the degree sequence of G and M is equal to D divided by the probability that the degree sequence of G and M is equal to D minus EA plus EB is equal to some explicit formula, DB plus 1 over dA, 1 plus dB minus dA over dN times 1 plus M2, here it is again, of just D over dN. And the point is that here we get a plus big O of D squared over N squared. And this is true. What am I using? Well, I'm using the concentration lemma. So let's say that N log N is comfortably below M and no upper bound. But what is the point about this D squared over N squared? So the point is that if D is little o of N to the 2/5 over, I think, log N to the 5th, then this D squared over N squared is little o of 1 over the diameter of S. Okay, it's a calculation you have to do. So we have the diameter here, and I tell you, well, there's a way to get this formula. Whatever it is, the point is the error is D squared N squared. And if my D squared is not too big, then this D squared N squared is little of 1 over the diameter. Why is that important? Well, I'm claiming that this is enough to finish our first goal of getting a good approximation of the ratios of any two sequences in here, right? Because let's say I have my D, some D, and I want to get the ratio to some D prime. Then what do? I find my path, my shortest path connecting these in this local change graph S. And along this, I have a very precise formula for the ratio. And that is so precise that I can multiply the errors along these ratios and get a formula of the ratio, whatever it is, with relative error little of 1. Okay? So the point here is that for arbitrary sequences, let's say this is like D0 on my shortest path, this is D1 on my shortest path, and so on, and this is like at dr. So I find my shortest path, and I can write the probability of d in GNM over the probability of d prime in GNM as a telescoping product of these adjacent ratios. So the product I equals 0 up to r minus 1, the probability of d I over the probability of d I plus 1. Each of these I get with a relative error of 1 over diameter. So the total, this gives me some formula which is correct up to order 1 plus little o 1. Okay? Okay, how much time? Okay. Good. So I think this is a good place to stop because, yeah, now, so what we want to do from here is to prove this lemma. And that's really the whole goal of this whole argument, like to get this really precise approximation for these adjacent ratios. So let's start this tomorrow fresh.